Hello, how are you? How are your children? They are better?
Yes.
That's nice. Okay, good. Oh, by the way, for you still don't have a group. But you have a group of you. Actually, myself. No, so with another person, it's more complicated. Okay. But you also, Moshkan, you need to find a group. Ah, right. But didn't I send you the PDF? I didn't. So you should tell me.
Because I was missing some.
Ah, okay, okay. Yeah. Okay, okay. So you didn't. So let me see. Sorry? It is on the either the 17th, not 7th, sorry. Either on the 23rd of January, you can present it on the 23rd. That's the what we call regular season. That's the date of the exam. So 23rd of January, or if you want to postpone, you can do it on the 7th of February. Okay? 7th of February. It will be a presentation like the others. Okay? But you should find some people. Sim, ou normal ou recurso. Não, nada. É só. Acho que ninguém vai apresentar na normal porque falta pouco tempo. No exam, just the assignments.
Just present us.
Yes, just present the assignment, nothing special. Okay, what else? I'm lost.
I know the name.
The girl with glasses, she's Anna, yeah. Anna Poços. You want her email? You want her email? If she, yeah, I think you can contact them. Yeah, I think they are 5, but since you are not officially registered, you can do a group with them if you want. You can contact them. Let me see, right? I have her number, so you contact her. If they are okay with it, you can do it with them. Okay, no problem. Egino, you are in Italy. Okay. Yes, last lesson. Yeah, yeah. Today is the last one. But in any case, I will. If you need, if many students ask for, I can give a Zoom meeting or something. It's a Zoom call just to help with the assignment. Okay. Egino, can you hear me? Let me see if I can listen to Egino. Sorry, can you speak again?
Yes.
Ah, got it. So I was just wondering because I don't think you have a group yet, do you?
No, not yet. No.
Ah, okay. So you should try to find someone.
Yeah, okay. I will send some email.
Okay, so let me show you who's available still. UA. Now, classes. 23. Okay, long way. So here you can see the people who are available, and perhaps you can send them an email. Okay, so up here, everyone is assigned already, and you have this, wherever you have empty group here, are people who are still open for having a group.
Okay, thank you.
So you can, if you want, you can print screen this, and then you send an email to those people, see if you can find.
Okay, yes.
Okay. Ah, já está confirmado, mas o João disse que ainda não tinha certeza, que ele ainda não tinha respondido.
Ia falar primeiro com o João, depois falar com o João, e mandei mensagem ao Fábio.
Pronto, já está confirmado, não é? Então vocês são o 11. É que o Fábio no 11, não é? Okay, so Gino, you should try to contact these people to see if you can work with them. Mosgani is here, and I think she also doesn't have a group. And the other people are João Bastos, João Figueiredo. But anyways, you try to email. I know Mosgani is already with someone, probably, right? Yeah. Anyways, if you can't find anyone, talk to me, okay? Even if you need, you will do with an old group or something like that, okay?
Okay, thank you.
Okay, I will cut the sound now, Eugene. Okay, if you need, you contact me through the chat. See you. Have a nice flight back.
Thank you.
Eugene já está. Então, Miguel, está aqui. Miguel Tavares, não é? Então você é o 12, salvo erro. Não há nenhum 12. Exato, 12, já está. Pronto. Mosgan, then you will have to send me an email to confirm, okay? You with Anne or something like this. Okay, so today, what we are going to do is continue to, by the way, only Magda was in the theoretical class, right? Miguel and Mosgan were not there. Gino, I'm not sure. So what we were working, well, for the two of you at least, we already have the assignments PDF or script. This is what you should do. This is the apartment, and there are some examples of missions that you should do here. So you can just, for example, a mission would be go to the small room and search for a red sphere, something like this, okay? Or check if someone is home. And all these missions that you are supposed to try to do, these missions are for the robot to carry out, of course, and these missions that you are supposed to do all require movement, navigation. So the robot must navigate around the apartment. And that's what we are going to be talking about today, okay? So part 13 is about navigation. So exercises 1 and 2, I did them in the theoretical class. So the first one is about odometry. Odometry is a way of localization by counting the turns of the wheels, okay, of the robot. It's like counting our steps, like a treasure map. And then we did this exercise 2, localization with Gmapping. So I can start with 2 very fast, so just so you can see. So the first thing is that we need to install the Gmapping with this command, and then we are going to create a map by doing SLAM. SLAM means simultaneous localization and mapping, and it's a procedure that will create a map at the same time that the robot is localizing itself on the map that it is creating. I can show you how it works, and it's much easier to understand. So if I launch my gazebo here, I can launch my gazebo here, perhaps. So gazebo, that will be, so robot will bring up gazebo, that's the apartment. Okay, so now we have the apartment. Now we have to spawn the robot somewhere in the apartment. For that, we already have the launch file, robot will bring up. So if I do robot will bring up.launch, we have our robot is spawned, okay? Now, if you want to see something, we have to tell in RVs that we want to see from the base link, for example. And with this, we will see where the robot is and the data from the LiDAR. What we have here in terms of geometric transformations is the following. RQT,
So right now we have the base footprint and also an odom link. This odom link is simulating an odometry that exists on the robot because the robot is simulated. So is the odometry. So it's simulated by the gazebo. So gazebo is publishing transformations from the odom coordinate frame, the base footprint, which are changing as the robot moves around.
We can assume the bounding systems are all like
We can assume what, sir?
the systems are all like
Well, if you put some noise, it will be better. Shouldn't make a lot of difference. So if you take a look at my system here, you can see the flickering in the data. That's because I added some noise in the chakra. Right? I can show you. Gazebo, chakra. So even though it's simulated, the sensors will have some noise. You can see here blah, 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 noise of type caution with some standard deviation. Yeah, also you can put some noise in the odometry. Yeah. Yeah, clearly, in the case of the odometry, in the real counterpart, it always has noise and it's a problem. In the simulation, you can configure it to have very little noise or none at all. I'm searching for the odometry, it's here. So the noise here, I don't think you can configure it. Yeah, so you don't have noise in the odometry anyway. There is no way to configure it. So no noise, you are very lucky because typically the odometry is not so nice. But in any case, we are considering the fact that the odometry is noisy because we are not relying on it completely. So we are going to use the odometry, yes, but only to provide an initial guess for the other localizers. Okay. Now, how to create a map? So we have to run the gmapping node with something like this. So we are going to run the gmapping ROS package, the slum gmapping script, mapping the scan to the /scan, that's our topic for the LiDAR data, and then our base frame to the base footprint. Why am I doing this? Because in the gmapping tutorials, you can see that, so if you read through the gmapping stuff, you will see that it requires the topic scan to be remapped to the topic name of the LiDAR. And then it has here some parameters, in particular, the base frame, which by default is base link. And in our case, the base frame is the system which is connected to the odometry. In our case, it's not the base link, it's the base footprint here in red. So we have to remap from base link to base footprint in order to have the gmapping work properly.
in the presentation here to map the department, or you can have the mapping already done, just
Yeah, definitely you should have a map already done. And perhaps I can ask you, just try to map a little bit, just to see, okay? But you should have as a backup a nice map which takes half an hour to do, and you will not have half an hour. Okay. So these are the things that I'm going to remap with gmapping. And now I'm going to start gmapping like this. So here we have our views, and here we can launch our gmapping like this. So copy paste, and what's happening now is that we have a map. So RVs is already showing this map because I've added this. Let me remove these ones and show you what's happening here. So I'm going to also remove these ones and add a map. As with any display, I have to configure it, in particular the topic, which is /map. So here's the map, okay? And so this map will show us what's occupied. Those are the red, the black stuff. What's empty, that's the white part, and the whatever is unknown, that's the gray part. And now we can move the robot around with our steering, which I don't know. Here it is. So we can move the robot around now. And as I'm moving the robot around, the localization, the SLAM, simultaneous localization mapping, will continue to localize the robot in the current map. So it will know where the robot is currently with respect to the map that it's storing. And furthermore, it will, at the same time, simultaneously, update the map. So continue to the mapping procedure. So look, I'm moving around, and if all goes well, it's just being able to map. Okay. Oops. Okay. So it's moving around the hallway and it's mapping the scenario. Let me zoom out. It's mapping the scenario. Okay. Okay. I think I'm bumping into the wall. Okay, now it localized well again. There was a point where it didn't really, so that you can see that the scans are not very properly aligned right now. So it's trying to localize, not perfectly. It's okay, now it's okay. And it added a new scan to the map and so on and so forth. Of course, you will need to do this, traveling all the way through the apartment until you are, how to say, satisfied that you already have a nice map which you can work with. Okay, I'm just going to go around this to the kitchen. Okay. Oops, bumped into a chair, I think. Okay, so now. Okay, so that's not a perfect one. Of course, you would need to go to the balcony, to the rooms, and to the bathroom, to the, yeah, everything. Now, after we have a perfect map or a complete map, what can we do? So we have to save it because we want to use it offline. The map is being stored in something called a map saver, the map server. And so this map server is a ROS node, which is running now. So we can ask the map server, not running, we have to call it, and let me show you how. Map server POS. So this map server has an option to save the current map, save to a file, which is this one, ROS run map server, map saver, and then the name of the map. So I'm going to save the map into the new ROS package that I've created called Robotler Navigation. So I have here my maps, and I have here, let me create a new folder for Aula P2. Okay. So what I'm going to do is I'm going directly to that place, which is Robotler Navigation /maps Aula P2. Okay, so I'm there, and now I'm going to call the script ROS run map server map saver -add, and let's call it map instead of my map. So right now what I did was I recorded this map, and I have a YAML and an image file. The image will contain the map. Okay, it's a drawing of the map, and in this YAML you have additional properties. For example, the name of the image, the resolution of the map, and so on and so forth. Okay, so this go ahead again. So this resolution, for example, is 5 centimeters, which perhaps is too much. Perhaps you can think of changing the resolution to a smaller resolution, because if you consider these hallways, 5 centimeters is actually quite a lot. It means that each of these blocks has 5 centimeters side by side. I'm not sure if it's too much. You can try with smaller resolutions. I mean, we can try it now. We already saved, right? So we can try to do a new map with a smaller resolution just to see how it goes. So if I delete my robot, just so I can bring it up again. Robot blur bring up of launch. Again, we have a robot. Then the robot steering will go this way, okay, or yeah, that way. Or this, no. Okay, something went wrong. Let's try again. That's strange. RVS is failing. What? Oh. I said. Okay, so I have a problem not with RVS, but with something else, which is this steering. I hate this steering because it creates a new window, which I hate. Anyways, I got it now. And we have the RVs again. Now we can start the G mapping once again, but before we start the G mapping, let's change the resolution. So if we go back to G mapping, there should be a parameter here which will define the resolution of the map. Let's search for it. Step by step iterations. Yes, yes. Well, you have to. It's two processes or many more processes, but actually, Gazebo is replacing the real robot. It's a simulator, and our system, which is called G mapping now, is doing the SLAM. But it's doing the SLAM, what we call in an agnostic fashion. What does it mean? It means that it's processing data from Gazebo as if it was data from the real robot. So G mapping doesn't really know if it's processing data from real data or simulated data. It's the same for him. He's agnostic to it. He's just processing data and trying to localize and create a map. We are doing it with Gazebo, with a simulator, because it's easier to teach and because we don't have robots for everyone. Okay, that's it. So I was looking for the resolution. Let's see if I can find it. Resolution, angular sampling, no. Delta, resolution of the map in meters per occupancy grid block. So let's try to go from 0.05 to 0.01, okay? So I have to change the delta parameter. So now I'm going to launch again the G mapping, changing the delta parameter to 0.01, 1 centimeter per cell. And now we can take a look at what's happening here. So now let's move it over to. Okay, so now you can see that this is a much more detailed map. What's the problem with this map? You need more computing power, okay? That's the problem, of course. So now I'm moving around, but I think, yeah, well, it's still working, so it's not so, it still works, that's good. But when we start doing the map of the whole apartment, I'm not sure if it's going to be too much. Just to say, don't trust on the parameters that I give you by default, because there's no guarantee that those are the better ones. Those are just the ones that I used. And I don't explore, I just show you what is possible. Okay, so here you can see a map with a much different resolution, okay? So here, for example, you can see that the black cells, which are the regions of occupied obstacles, are much smaller, of course, 1 centimeter wide. Okay, so you should try a resolution, perhaps a different one, but let's use the one that we saved before of 5 centimeters. Okay, so now let's wrap up the part about creating the map. That means that we have exercise 2 done. Now what we need to do is go into exercise 3. So we want to do localization without mapping. Why are we interested in this? Because simultaneous localization and mapping, which is what we just did, is not so accurate, so often it fails. And also, for our purpose, for example, we have a mission where we want to go to the office and find out if there is a computer there. So we need to have the complete map created in order to know how to get to the office. So we cannot be creating the map as we are moving around. So we need a complete map like this that I'm showing here in the image in order to do the missions that are for the assignment. So we are going to do this map that we created offline. And in this stage, we are going to localize in that map without updating the map. So we are not doing simultaneous localization and mapping. We are just doing localization, okay? So we are just going to localize. That's exercise 3. For localization, we need to use the AMCL package. So AMCL is a package that uses particle filters. So particle filters are an algorithm that is used to keep track of several hypotheses of something as the process is moving forward in time. In this case, each particle is a pose. A robot pose is not just a pose, it's the position plus the orientation. So what happens when we use AMCL is that it will keep track, it will maintain several hypotheses of where the robot should be, of robot poses. So it says, okay, perhaps the robot is here, perhaps the robot is there, and perhaps the robot is over there somewhere. And these particles will be tested with what comes forward in the future. So I have three hypotheses, and now the robot starts moving. When the robot starts moving, I can say, okay, so if I was there and I'm moving forward, I should be seeing a window just ahead. And as I move forward and I do not see a window, that means that that hypothesis has a very low probability of being the correct one, right? So in that case, that hypothesis will lower its probability, perhaps to a point where the hypothesis is destroyed, is discarded. So perhaps there is another example of an hypothesis where when the robot moves, I'm going to see what I'm expecting to see. And if that's the case, the probability of that hypothesis will raise, okay? So this, just to say that this is a very complex mechanism of keeping track of several hypotheses over time. It's really nice, this algorithm, I think. And I can show you how it works, but perhaps it's better that I show you the animation because it's much easier to understand. So just bear in mind now that we have several hypotheses of where the robot should be with this algorithm, we just have to launch it. How can we launch it? Well, first thing, in order to launch it, we need to have a map. And for that, we need to launch the map that we've just saved with this. So ROS run map server, blah, blah, blah. So first thing, I'm going to launch the map. In order to launch the map, I will go to the roboter navigation, that's where I went, maps, and here I have the Aula P2. And so now I'm going to say ROS run map server, and it's the map.yaml, my map. So right now I'm serving the map for that we saved before. Although I needed RVs, okay, so let me run RVs again. Not first, it's the same. Spawn service failed. Eu tenho que desligar esta cena que eu já estou ficando isto. Okay. Okay, so you can see here. This is the map that we created before, okay? Or not, perhaps not. Because we need to, yes, it is, because we just loaded it here, okay. So this is the map that we created. We can show it just by doing this display map, okay, like we had before. And so now we have the map that we created. This is a 2D map, of course. Now, for the localization part, what do we need to do? We need to start the AMCL node. Typically, it has many parameters. I will try to launch the minimum set of parameters that we actually need. So the first thing that we need is to define the scan topic. In our case, it's /scan. Second thing we need is to define this blah, 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 blah. Let me search, where is it? Here. This base frame ID is where the robot's base is, and by default it's base link, but in our case it's base footprint. So let's change this one to base footprint as well. So base, it's a parameter, so base frame ID to base footprint. Okay. I think that should be it. Sorry. Run, AMCL. Okay. So what happened now? Now the system is running, the localization system is running. And if you go to Gazebo, you can actually see two things. You can see the map, and now you can see the robot. Before you couldn't see the robot. Why can you see the robot now? because now the localization is publishing a connection between the map and the odometry, which is here. So now this was before we have localization. This is when we have localization. So this part here is being published by AMCL. It publishes from map to odometer, okay? Now, of course, that if you take a look at RVs, it's publishing a completely wrong hypothesis of positioning. But as I told you before, it has many hypotheses, which we can actually see if we check this pose array. So if you check the particle cloud topic, it has an array of poses, so many poses, where it thinks the robot should be. And the place where the robot is now represented is where is the hypothesis with the maximum probability. That's the one that is being published to the end. Okay. Now, if you take a look at the real robot is here in Gazebo. Where is the robot? I'm lost. Oh, it's there. Okay. So let's put it in front of. I'm just going to change it. Okay. So it's here near the TV and in the room, the dining room. And right now, the localization system is really confused. It doesn't really know where the robot is. But we can help the system manually by giving what they call a pose estimate. So we can say, oh, I know that the robot is more or less here. So if I do this, you can actually see that these red dots, which perhaps red is not a good color. Let me change the color to color transformer flat. Let's do yellow, for example. You can see that these yellow dots here are better aligned, not perfect, but better aligned with the walls. Okay. That's okay. So if I try to improve my estimate, for example, like this, it's getting better, okay? But still, the system is quite confused. Okay, it has many poses near the place where I said, this should be the pose. So it used my information not to scatter the poses everywhere in the map, but only near to where I said it was. And now it is able to refine the poses as I start moving. So as the robot starts moving, it's going to say, okay, the robot is, so for example, look at this pose that I'm highlighting with my mouse. It says, perhaps the robot is close to the wall. Now, if I start moving forward, the robot would bump into the wall and would not be able to move forward anymore. So that hypothesis, after some time, will surely be discarded, okay? So let's see how this evolves. So now I'm going to drive the robot around. So I'm just driving. Also notice that the yellow LiDAR data is aligning better with the map. Now it's getting better, you see? And what's happening in the cloud of hypotheses is that it's shrinking because the system is getting more and more confident that that's the place where the robot actually is. So the hypotheses that it's maintaining, that it's not discarding, are only the ones close to that area, okay? So let's move around again. So now we have a very good localization. The system is being able to say, okay, I'm here and I'm almost sure about it, okay? You can see that the localization is fine because the place where the system positions the robot has to do with the hypothesis of the maximum probability of where the localization thinks the robot is. And then the LiDAR data will be based on that. So the alignment between the yellows and the black ones is almost perfect. That means the localization is working very good, okay? And, okay, so now you have the localization working. It's not so difficult. So I can drive around, no problem. It works fine. And it's still localizing properly. See? Now, what can we do now? We can, of course, this localization is a global localization, which means that if for some reason I now move my robot from one place to the other, it's going to realize that the LiDAR data doesn't really align properly with the map. So if I pick up the robot, like I did before, if if I pick up the robot and I just move it back to the TV, the system will say, I'm completely lost because this should be properly aligned and it's really not aligned. So if I move the robot around, it says, no, wait, I was there, I should have been there. And now what I'm seeing in my LiDAR data is completely different from what I should be seeing based on the place where I think I am in the map. So what it did, according to this reasoning, was I'm going to scatter my hypothesis. I'm going to generate new hypotheses in many different places. So now I would have to help the system again by doing a pose estimate like this, something like this. Okay, so look, you are close to this place. Now, if I move around, perhaps it will be able to localize again. It's getting better, I think. Oops, sorry. Okay, so reverse, move. Okay, now it's getting better. Okay, so this is a crucial component of your system. It must be able to localize. This is how actually these Roomba robots work. The vacuum cleaners, autonomous robots at home, they work by doing SLAM, okay? And this kind of thing. What we need now, after this, is to be able to move the robot around. So, don't forget, I launched two things, the map server and the localization. So I can just, what I did was I created a launch file where I'm starting the map server, okay? In a particular map, in this case, it was the M-ring map. I'm going to say Aula P2 map. That's the map that we built. This is starting the map server. We did it here on the right-hand, on the left-hand side. Then the second thing is to start the MCL. We are doing it here. We are starting a MCL with many, many different parameters. I just copied this somewhere from the internet. The important ones that I changed were the ones that I changed when we launched the system through the command line here. It was the scan, which must be the /scan, and the base frame ID, which must be the base footprint. So here, if you take a look, the scan is an argument which by default is /scan, and the base frame ID is the base footprint, okay? Then you have many other parameters. I'm really not sure what they all do. You have to test and try and see what happens. So this is clearly one. So it's the maximum number of particles and the minimum number that the system should keep. For example, if you put 30,000 instead of 3,000, what will happen is that the system will have many more particles, but will of course be much slower. Let's try it. So now I'm going to launch the localization through the launch file instead of through these two things. So ROS launch, robot load bring up, navigation, localization. Map server could not, I made a mistake, okay. Let's try again. Spawn service, no, pardon. Okay, now again, we have to delete our robot. First we delete our robot, then we spawn the robot here. Não seria, Miguel, que já me apetece tirar o computador pela janela. Pronto, isto aqui já não está deitado. Ok?
Já percebi que vou dizer que está melhorando a interface.
Exato.
A ligação toda com melhorar a interface.
Melhorar a interface. Se você melhorar alguma coisa, fixe.
A aplicação. Se usar a aplicação, a interface.
Eu não costumo, sim, mas eu não costumo usar. Eu costumo usar um que dá só. Chama-se o Turtlebot TLL, Turtlebot 3 TLL. E não tem esta parte de interface, porque na verdade uso sempre as teclas. Sim, mas aí tem que ligar o Android, não sei o quê, é mais fácil, eu prefiro ligar no terminal e mexer com as teclas. Aliás, posso fazer isso agora, vou fechar este. Sim, talvez. Mas eu gosto mais de fazer assim, vou mostrar. Okay, so localization. Now with many particles, 30,000, perhaps it's too much, but let's see. Okay. So where are the, so let's see the pose array. Okay, now we are waiting for the system to process because 30,000 is too much. Okay. So perhaps 30,000 was too much. Come on. Okay. So you can see many particles. And now to drive, I do this, Miguel. I do was run. Actually, I did the script already, row butler, but I can show you the default one. Was run turtlebot 3 teleop key, and I put a small window like this, and well, not so small. I can just drive it around like this with my keys. So you can see now that we have many more particles, which are being discarded and deleted and so on and so forth as the robot is moving. Actually, the system is still working with 30,000. That's nice. I think this computer is very good. Perhaps it's because of that. But it's working. That's nice. Okay. Now, something else that I could try to show you is this. So we can also see the pose with covariance. In this case, the representation is this sphere or ellipse is the uncertainty in position. So the wider the ellipse, the violet ellipse, the purple ellipse, the less certain about the position the localization is. And this angle, this cone, yellow cone, is the uncertainty in terms of angle, okay? So if I kidnap the robot once again, you will see that the uncertainty should change. For example, if I say, you are here, the uncertainty expanded very widely to say, I'm really not sure about where I am, of course, okay? Okay, let me localize the system so that we can then try to do the navigation. Oh, I'm going into the kitchen. Oh, it's getting there. Ah, it is being able to localize. Nice. It recovered. Oops. Okay, so now we have our system again localized. That's nice. And now we are going to go into the movement part. For that, we use something in, so we are in exercise 4 already now, navigation. So you are going to use the ROS navigation stack, in particular, something called the move base. There's a lot to read here, so you should read it, but we are going to use something called move base. ROS move base. Move base, okay? So the move base is the ROS navigation, is the planner. So what does it do? It will control, it will drive the robot automatically. It will receive as input information from the AMCL. So this will give the planner, the move base, information about where the robot is. So that's the localization. And then also it will use odometry. And moreover, it will receive information from the map, of course, and from sensors. Okay, so inputs, localization, the map, and sensors. Output, where to go. MoveBase does this using a global planner and a local planner. So it has a global map of where it should go, and then a local map. Why do we need a local map and not just a single map? Because a global map has to do with the offline map that we have. So imagine this room, I map it, and I want to go there. So if I want to go there, I create a plan saying, okay, I can go to the middle of the hallway over there. So now I start, that's my global plan, and I start going. Now, if, for example, I do this plan and I start going, at some point, Miguel stands up and is in the middle of the path. So I can't go through this place because there is a temporary obstacle in the middle. So perhaps this, in my local plan, I will say I want to go there, but there is an obstacle here, so I can just drive around. So the local planner is for driving around obstacles. The global one is for giving you a global plan. Okay. How can you then? So there is a lot of stuff that you can unpack here. I'm just going to tell you how it works. So the way to trigger an action is to set up a goal to say, okay, I want you to go there. Okay. And what the system will do is it will publish velocity commands, which are in fact what we are publishing when we drive the robot manually. So the automatic driving will replace the teleoperation, which makes sense. So how can we launch this? Well, we can launch it by using this launch file that I have here, which has the following. Look. So I have my velocity command topic, and in our case, it's the /cmdval. That's okay. ODOM topic, it's the same. Move forward only, true. Okay. Now, here I am launching the move base node. And then I'm defining that I'm going to use a planner. So that's an algorithm for doing the planning, which is the DWA. And finally, we have many files, which are all inside the param folder, where we can configure how the navigation works. So all these files here, 1, 2, 3, 4, 5, have properties that we can change in order to have this or that navigation. Let's start with the first one. So cost map. Common parameters. In here, we can define how the obstacles are inflated and the footprint of the robot. We will see this too in a moment. And below, we define how the system receives information. So the sensor frame ID is base scan, the data type is laser scan, and we have the topic /scan. Then this one is to define how the planner actually works. So for example, you can define the maximum and the minimum velocity and many other things, okay? Then you have global cost map parameters, which are the update frequency and many other things, also for the local cost map, okay? And finally, you have the move base parameters, which will define the patience and the controller frequency and so on and so forth. So a gazillion parameters. Most of them, we don't really know what they do, but first let's start the system with these default values for the parameters and see what happens. And then we try to change this and that parameter, okay? So in order to launch this, is just ROS launch, move base. So I'm going to launch it here. So the navigation now here, this is going to be navigation. So ROS launch. Roboter, navigation, move base. Okay, so now if you take a look at this, what are we seeing here? So first let me delete, not delete, but so what we are seeing here is the map, and we have here, this map is on the topic global cost map. So the global cost map is this one, where we have obstacles that is, so a high cost is black or gray, a low cost is white. So white, the robot can travel on, gray, the robot shouldn't travel on, black, the robot cannot travel on, okay? So this is the cost map that the global planner uses, and we are seeing it here. Then we have a local cost map, which we can see here, okay? So right now it's local, so it's only close to the robot. It says, oh, there is an obstacle here, an obstacle there. And we can actually see them both together. So we are going to show the global one, and we are going to add a new one. Oh, it's there. No. We need to add a new map for the, so this is the global, yes. Sorry, duplicate. So this is going to be renamed the global map. And this is going to be renamed the local map. So for the global map, I'm going to put this on topic global cost map. And for the local map, I'm going to put this on topic local cost map, and I'm going to change the color scheme. So we have something like this, okay? Actually, no, not, okay, so this one. So the red and the cyan are the cost maps, the local cost map. And so when we start planning, we will see also a path which is on topic global plan in green. So the green is the global path. So I want to go from there to there globally. And so this is the global path. I can rename it. And then we have here the local path. The local path we have in blue, okay? On topic local plan. So there is only one thing more that we need to see, which is this polygon. This polygon is the shape or the projected area of the robot onto the ground, which is used to in order to see if the robot fits around the obstacles. So we can see this polygon here. Right now, it's this thing that we defined here. Okay, so you can see it there. I just defined it to be a little wider than the robot. And finally, we can, so notice, the whole system is running. So we have the planner up and running. It's in this terminal, but it's not operating, it's idle. That means that if you don't give me a goal, I shouldn't plan anything. So I'm not going to move if you don't tell me move there. Now we give a goal with the 2D nav goal, saying go there with this orientation. And the system starts going. Okay? And we can actually, oops, sorry. So let's try to go somewhere else. Go here with that orientation. You can see the green is the global plan, the blue is the local plan. Okay. Yeah? Acho que nunca vi. Aliás, one of the problems that I have is making it fit around the hallways. So this is not operating. So this is already on GitHub. You can use it, but it's not perfect. So it's not going to work perfectly. You have to configure it to try to make it work better. Okay. For example, I can, so what's the difference between the global map and the local map? The global map is an offline map, the local map is an online map. What does it mean? It means, for example, that if I tell you, go here, is offline, is local is online, and the global is offline. So it's like your GPS. In the GPS, you have your roads, but if the road is blocked, the GPS will not know it, right? So you can, for example, how can I show you this? I can show you if, for example, all of a sudden, oops, I did something wrong. I changed the road. I think the localization now is going to go crazy. Let's see. Yeah. Let's see. Let me try to drive the robot around. Well, I think it's still more or less okay. Okay, so I was trying to tell you, look, the local map, the one that you see in cyan and red, is dynamic, it's online. What does it mean? It means that if I, for example, pick up this chair and put it there in front of the robot, I'm okay, now this is chaos, okay. I hate this sofa. Okay, now it's gone. And I'm going to put this up. Well, let's drive close to the chair. So now we are going to drive close to the chair. So I'm going to turn around. I'm trying to drive, but I'm not being very successful driving. It's strange. The chair is here in the global map also. It's there. So it's apparently the global map is also online. I thought it was offline, but it's being updated, you see? So look. Yeah, go ahead, Miguel.
Right.
Sorry?
It's the cost map of the.
Yeah, it's a cost map, right? Yeah, so the map that we saved doesn't have the chair there. Sure, that's the one I'm showing now. Now the global map for the planet does have this obstacle, and the local map also has the obstacle. So, in fact, I'm not really sure because the global map is also dynamic. So I'm not really sure what's the difference between both the global and the local one. In any ways, we can drive the robot around, like you see. Okay, so again, go there. There he goes. As I told you, this is not working perfectly because, for example, something that would be very easy, which is go back. So this is a differential robot. It means that it can drive, it can rotate around itself, right? So if I tell him go here, it should stop and start turning around and go back. And it doesn't do this. And in the end, I think the plan will fail. So it's trying to find space to turn around instead of just turning around. Which is kind of weird. I don't know why this is happening, but this is something that you can investigate and try to make it work. So I give you 75% of what you will need. So you can see got new plan, but it's really not being able to get to the target pose. Actually, we can show the target pose as pose. Where is the pose? Yeah, here. So this is the goal. That's where we want to go. And I'm just going to show a topic here. Ways. I'm not sure which one is the correct one. Oh, now it's rotating. This is a backup plan. So it's not being able to find a way to the goal. So now it's just rotating around to see if it can somehow. This is a failure. There is a name for this. I forget the name. I think the plan will fail. Okay, no plan, no plan, no plan, and so on and so forth. So I can just stop move base, okay? Drive the robot around, for example. Come back here. I think it's okay. Localization is correct. Okay, so now we can try again with the movement. Okay, and now after this goal pose that I have here, let's change the color. Say something green, for example, or the sky is blue. That's okay. And if we say here to the nav goal, okay, now we have this arrow there, which is nice. That gives an idea of where we told him that we want him to go, or it to go. And Okay, so almost everything is working apart from moving around. Okay. Now I don't know why it's not moving. Got a new plan. Got a new plan. Perhaps it's because of this guy. Yeah, it's because of this guy. I cannot have the teleop because otherwise the teleoperation will be sending messages saying velocity zero, while the other plan is saying velocity something. So they will conflict. So I have to shut this one down. Okay, so this is more or less working. Now your job is to make this, to try to get this far and then do the assignment, meaning somehow be in the kitchen and say, let's go to the room and find something in the bed or something in the table, something like this, okay? Okay, so you can try it now, and if you have some questions, let me know, okay? You know where to start, right? You should start from this script, from part 13. Yeah, start from the beginning, that's the first part. Exercise 1 if you didn't do anything yet.
Mário, você não quer dizer agora?
É, mas depois de hoje
É às 12h30. Yes. Se não forem, metes no launchpad. Sim, sim. Mas em boa verdade, isso foi uma solução de coisas que qualquer coisa. Não. O critério talvez seja por mais desculpa, por mais receber, tempo de código, mas não é assim nada de uma maneira ou de outra. Ou seja,
Não.
maybe because of the end of the year or something.
Yes, I changed my passport, but again, I changed the passport.
Not working. This is one of these.
Yes, yes.
Really new words. Yeah, try to. You are sure not making the other, not that you wrong password.
Yes, I'm sure because I now page again. Yes.
Still trying. Look at this account. Cancel. And we step on so there. Forget. Okay, now. Should get the other one. Yeah, now go again there. Click. Then let's pick a new one. When we move there. Quite a sense. Not only to other units. Yeah, yes. Okay, so this is the PEP. So try using image. You can start to move to it's working. Okay. Vocês não querem luz? Não? Morcegos, não. Moshe, so this year you are not registered officially, right? So. I think it's helpful. We can have one more course. So if you want, you can try to roll this through. And then you know, the grade that you have. Understand?
Yes, I understand.
So
Actually, I finished my courses for my PhD program.
but you can do extra. It's just something that you can have next year without no extra cost, without extra words. In the CV, say, I think this course,
For my CV, yes. Just I want to learn this course for my PhD program.
and so you what is your PhD work?
About language charging for mobile service provider.
Mobile service.
Mobile service provider.
The first one I did. And I was checking. And then it was.
Actually, I am in middle of lots of things that I don't know about them.
Yeah.
Just I not finding lots of things.
Lots of things, yeah, because you're confused.
It's
And Professor Pedro also, that's nice.
that's it is very useful. But I as these courses step by step slowly
Yeah, it was,
because it's complicated.
yes, I know what to do. If you want, you can ask my help after the course.
I follow you.
Some-
Yes, even YouTube.
Well, like,
Actually, I have been part 9.
okay, nice. Oh, it is many people. When I ask if they like the classes on YouTube, I think many people like this. I should start charging every time they go there. No, but if you need some help, like wireless charging, it's. How does it work? Why is it dynamic wireless? Why dynamic? Just wireless.
Mobile service. No. They do some tests. They charge for all the time. You know, we want to have a network without stop.
Okay.
They have to do tests without stop, non-stop.
No stop up, yeah. Continuously up.
Yes.
Okay. And for that, we need to
And in the diagram, maybe, for example, one of us you walk from there to there. And suddenly it's charge speech.
Okay.
So our networks can be
Optimize.
yes, and actually it's
Okay.
kind of optimization.
But this, so it's like a big management. This now this one should go there because. Well, okay, okay. But how do you charge it? Because I don't know.
Because
Either with the month, but it's we charge by police. Just like the
yes, we have this kind of charge.
okay. This kind of charging, so it's not wireless in the sense that it's charging. When we did it, first of all, the
We have a stationary section for the two master robots. We have two master robots, but we have one station, next station. Master robots go to the station to charge. They go to the networks. Yes.
So they go.
Like sense networks are robots who charge the
They're always.
IoT.
Okay.
You know,
It's like those airplanes that we people.
yes.
It's nice.
But
So you have to do some kind of fleet management to control these charger robots, to meet the other robots, charge. How comes the charger will take up? They touch each other. I have a problem.
yes,
But this is going to be simulation in real.
simulation. That's something I should know about that. So in that time, just simulation,
Okay.
not real.
I think that's a good option. But
What
when
makes
computer simulation, it's more about the parts and less about the charting. So you don't have to worry about the physics. You just have to make sure that your robot is going to meet. Okay. So robot is very important.
yes. Mapping localization. Exactly.
Should give the assignment that I did last year. That would be helpful for you because it had multiple robots.
Yes.
I can show you. Let me show. Where can I show you? Are you on Zoom?
Yes.
Yes,
that's-
no? Okay, so let me show you.
that's it from it.
Okay. Well, you have time because I have to search in order to find, and it's always a big problem for me to find stuff. So let me search. Waiting. Phones. Daniel. William. Nothing. Moving up. Name. Wow. I wanted to show you, but it's not. Alpina, perhaps this one. No, it's Alpina.
This is the assignment for PSR.
For PSR, last year, yeah, and for another course some years ago. So the assignment was to play a game where, let me show you an example. So it's something like this. So you have several robots, and these robots are going to be playing a game. The game I call the game is it's like children who play hunting each other, like running and hunting and grabbing together.
Yes.
Okay, so imagine that this game like this with 3 teams. So team red needs to have people from team green, which needs to have people from team blue, which needs to have people from team red. So you have the concurrent objectives of trying. So if you are red, you have to hunt the green robots, but also you must run away from the blue ones. So, and then you have teammates and so on and so forth. So that was the game. The robots will be trying to hunt other robots and will flee from their hunters. Okay. So this would be helpful for you because first in robots, we didn't use the SWAN, we used our own path planning, which is very simple. Because for example, if you want to hunt the robot, what you need to do is move towards, just point your towards where it is. And the interesting part here was because if you want to use several robots, you are going to have to create what the next is. You cannot, for example, right now we are using CMD velocity. That's the velocity command for a robot. If we have 2 robots and you publish a velocity in the CMD velocity, they can't both be a split command, cannot be for both. So you're going to need to have to push the CMD velocity on top and together into the robots space, which we did here because we had 9 robots here. We had to call, for example, red 1 was the first robot, red 1 slash CMD velocity. We did all this, all the robots.
And they have a constant velocity.
No, it depends on the driver. Space the goes, no, which is driving that robot. So for each of these 9 robots, we have a process driving. Let me try to say it for you.
And each robot
It's a different process. It's like an agent. It has a different process, which is driving it only considering the information from the robot itself. So it's not, they are not being driven by the cloud by some cloud server. They are being driven by their own local, because that's what would happen in the real world, right? I will try to find the videos again. So let me see. Perhaps from, so perhaps from the other year I can find. Okay. Not sure because so SAVI means Advanced Industrial Vision Systems, and what I did, so the start of that course for me was I told them small industrial, big advanced. So I didn't do any kind of industrial application. What I did was advanced image processing and computer vision techniques. So I'm doing tracking. I'm doing learning, machine learning with PyTorch, neural networks, deep learning. What else? Image mosaicing. I'm not sure, because in your case, I think the perception, because you have a problem of fleet management and of motion planning, this kind of stuff. In that case, typically what people do, because they cannot do everything. So if you are not using a single robot, you have many. If you have to coordinate them, and if you have to motion plan their movements, it's already a lot of stuff. So what people usually do is they simplify the perception. So if your perception is simplified, perhaps you will not get a lot of interesting stuff from this course. But if you want to attend, no problem. I have no problem. You can start next year. You just email me. It's okay. No problem. You can access the slides and the videos also. If you want to attend, it's okay. So let me see if I can find the video. We have videos. So here's one example. So we call this an arena. That's a football field with obstacles around it. And they are just launching the complete system. I'm not sure. Okay, so the robots start in random positions. And then they start moving around because the game starts. So for example, here you can see blue 1 and blue 2 there. For example, so red hunts green, which hunts blue. So if the green hunts the blue, so you can see here, what happened was that the green one was close to blue 1. That means it hunted him because it touched him, and blue 2 actually went to this area where my mouse is, which is like the punishment area. You are there for 10 seconds just to, and then you have a score. That means, for example, that the greens are already winning. Let me show you another example. This was a nice game also, but I can do everything. So let's see this one. I think the apartment one is nicer. I'm not sure. Okay, so here with obstacles. So you can see here that, for example, the reds are hunting the greens. That green there is
The greens goes
to the blue. It's RGB. RGB, red, green, blue. So red, green, and blue, and red. So
follow itself. If they find a way by itself.
each node, so the students, they know the map and they know their sensor information from their own, not from the others.
Yes.
So they have to search. So this was done through color perception. So they have the image of the robot. They process the image to find, if I'm red, I'm hunting green. So I search for green in the image and I point towards green. Something like this. Another, yeah. It's very nice. Okay. So if you need some help with that of using multiple robots, let me know, because this may be helpful. Okay, 10 minutes. And you, Miguel, where are you? Sabe por que este tipo? Não. Porque o laser não funciona. Não funciona. Mas pode pôr junto, pode pôr uma câmara XD. Nem isso, para largar, pode ser muitas coisas. Aliás, então vou procurar aqui o trabalho de João Santos para você ver. Espera lá. Se calhar você quer ver isso. Sorry? Yeah, sure. É que isso estava cá, se não estava aí, agora já não sei onde é que está. Você está aí? Está na net? Não. Assim. Agora T3 e agora João Santos. Onde é que está o João? Tiago Pinha, acho que fez com o João. Este é do ano passado. Tiago Pinha? Ele é do MRSI. Mas isto depois, não sei se eles vão mostrar. Daqui está a ver o Red 2, está a caçar o green. Apontou para lá e vai a caminho para o caçar. Mas não era isto que eu queria mostrar. Eles tinham, esta malta tinha uma cena. em que eles usavam umas câmaras RGBD, mas que não puseram aqui o vídeo. Não, não está no vídeo. Eles querem usar câmaras RGBD.
Mas eu escolhi, mas a verdade é que é.
Ah, foi?
Foi para aqui,
Engraçado. Sabia. Ok. Ainda não se arrependeu?
não.
Ok.
Mas
E você, pô, nunca me fui meter e tal. Pois. Deixa eu ver aqui se eu arranjo a parte do 3D.
essa é uma coisa.
Sim, este é mais fácil por causa disso. Quer dizer, dá trabalho, mas
Sim.
não é estressante. A data do exame é sempre um stress. Não, não tenho. Estava aqui a ver se encontrar, mas não. Mas você pode vir ao Tiago, pá. É assim.
Primeiro, como é. Eu não consigo já.
Pois. Sim, aquele desfazamento. Yeah. Tchau. Ok, pá, ainda bem que você. Aliás, eu perguntei. Tchau, Higino.
Ciao, ciao.
Sorry, I can't hear you, but I imagine you said ciao. Let's see. Okay, now, can you say something now? Já foi. Eu, por acaso, na parte teórica, perguntei se